Oxford, and he was programming even before I was, actually. And he had some kind of weird 5-counter, 5-circle diffractometer, and you vowed after that never to have to program on the bare metal ever again.
Yeah, it was all done in machine code and minimal, isn't it?
But I think most of you know that Phil is one of the founders of CCP4, worked in data collection and processing, and today he's mostly going to talk about scaling of data. And
I'm talking about MOSFLM as well.
And excellent, thank you very much. So, MOSFLM, scaling, Aimless, he already participated in the panel. A general, all-around good guy. It turns out that I found out that he's the second bassoon-playing crystallographer that I know. At the end of the session, we'll have a quiz, and we'll figure out who is the other bassoon-playing crystallographer that I know. So, Phil, you have 45 minutes. We're going to use this clock right here. I will stand up and start haranguing you if you get too close. Okay? Thank you very much.
So I'm going to talk about MOSFLM and the CCP4 processing suite, really. Just before I start, how many people here have used MOSFLM or the iMOSFLM interface?
Is your microphone turned on?
I think so. Yeah. Yep. Yeah, that's quite a lot. Okay, so much of this will look familiar then, which is good. So you can, of course, use data reduction and integration in automatic pipelines, and a lot of people in the UK certainly use ZIA2, which is pretty good, actually. And for decent data sets, it works very well, but difficult cases, you really need to look at fine-tuning. What I'm going to do is go through a sort of practical guide, if you like, of which buttons to press, what you might think of. I've only got 45 minutes. I could easily take 3 hours over this talk, so it's going to be very sketchy, and I apologize for that in advance. Just to start off with, the way you would install all this stuff, if you're using SBGrid, it comes with it because it's part of CCP4. You can also get it independently from Harry's website. And in particular, on that website, there is a tutorial. And if you haven't used iMOSFLM, or you want to practice on it, I strongly advise, if you're interested, to work your way through that tutorial. It probably takes an hour or two, and it will teach you a lot more than I can talk about here. That's really for reference stuff. So how do you start it? The easiest way is in the CCP4 interface, click on Start iMOSFLM, which starts up a separate iMOSFLM process with the files, looking at files in your project and the output files that go there. You can also start it from the command line, and the files will be expected to be in or relative to the current directory. There are some pointy-clicky things icons that you can get from CCP4, but the trouble with that is you end up with files in random places, probably in your home directory where you don't want them. So when you first fire up iMOSFLM, you get this rather blank window, and you'll see down the left-hand side a series of icons, most of which are greyed out, which are the successive stages of analysis, which more or less is what Jim talked about this morning, of going through the processes of indexing, strategy, refinement, and integration. So the first step you would do on this is to get some images. So if you click on this, it opens a file browser, and you can search around for where your images are. And if you double-click on any one of these images, it will pick up all the things it thinks as a form of an image series. So you don't have to click all of them, you just click one of them, and it'll load all of them. And it'll also open the image display window, which I'll come to in a minute, for the first image. Now, unlike some other programs, MOSFLM tries to pick up everything it can from the image headers. So in most cases, the image headers that have come off your beamline or from your in-house data collection contain all the information that it needs to process it. This is not always the case, but it's typically the case. And that is, for instance, the the distance, the beam center, the image phi ranges. That some of these come up in the main window, some of them in the settings are pulled down for experiment settings. There's a lot of things here, and you can change them if necessary. But usually, if they're not right in the header, you can change them. One particular thing here is if it doesn't necessarily know that your spindle is going in the wrong direction, and you can tell it that it's backwards there. I don't know which beam lines that applies. I think one of the APS beam lines goes backwards. Is that right? I don't know. What can go wrong with this? Well, as I said, some of the information may be wrong. Here's one example where all the images apparently are from 180 to 180.5. How did that happen? Clearly this will not work, but if you click in the first range, edit the first one, it'll automatically fill in all the others as consecutive. You don't have to edit the whole list. So if things are going wrong, it's worth checking some of these things. I've tried to put a few slides in here, which is what can go wrong, of things I've seen go wrong. People are endlessly inventive at finding new ways of making it go wrong. One of the really useful things about iMOSFLM is the image display, and this provides a lot of tools for looking at your images, including just looking at any single images, superimposing predicted patterns, found spots, and all the sort of things you would expect. And it's really useful, I think. It's great to put your data into ZIA2 or XDS or any other black box, and with good data, and the nice things come out at the end. But looking at the actual images is very informative when things are bad. So here's a couple of things. The tutorial takes you through a lot of things you can do with this, and I don't have time to do this, but two important things. Here is a case, you display the main beam position, and it's clearly not right there. And Jim showed some nice ways of finding the main beam, but actually in this case, if you just drag it using this tool into the middle of the beam stop shadow, that very often works, and it does in this case actually. And the other important thing that's useful is to manually mask out the beam stop shadow. MOSFLM does not automatically unmask the beam stop shadow. I know Harry has tried various algorithms for doing it, but has never been confident enough of any of them that they actually work. So it's your job to do that. And if you don't, you may well get some spurious things. You can, as I say here, you can do all the usual things of zooming and panning and look at the images and work out what resolution things are at, and very useful. So if you do the tutorial, it's worth playing around with the tools and looking at what you can do with this. So going back to we've loaded some images, we've looked at the first image, maybe some other images. The next step is indexing, and Jim described very nicely this morning what you're actually doing here. MOSFLM uses the Stellar-Rossmann algorithms, the 1D Fouriers. In fact, he uses their code, to be honest. So if you go into the indexing, it'll automatically choose two images that are roughly 90 degrees apart. You can change this, you can use as many images as you want there. It'll spot search them, and this is a summary of the spots. But if you go back to the image display, you can look at the actual spots it's found. And then it will try to index them. And it'll list the 44 possible lattice settings. It is 44, isn't it? Characteristic lattices. Which are basically... The one thing you should note about this is it's basically, they're all the same indexing solution. They're all the same triclinic indexing solution with lattice symmetry imposed on them. That is the constraints of the lattice of the cell unit cells. What it will do is it ranks them in the order of a penalty. This is how much they deviate from from the cells that you would require for that lattice type, like 90-degree angles, for instance. And it will pick automatically the highest symmetry with the lowest penalty. Typically, you get a sudden jump in penalty if you order them like this. So in this case, it's chosen the monoclinic lattice, which is actually right. But there are a couple of other things about it, whether we'll go into whether you think it's right or not. One of the other parameter that's really important to look at is this positional residual, which is in millimeters, and this is very high. And the reason it's high in this case is because there are actually two lattices in these images, and I'll come back to that. But this is, if you look at the predicted pattern, this is basically right, but not very good. You can also get a first shot at the mosaicity, the reflection width here. And this is the total, unlike XDS, this is the total reflection width rather than the Gaussian parameter. So they're different numbers. And it'll give you the space group. Monoclinic will give you P2, but if you know it's P21, you can select it. What can go wrong with this? Well, indexing is the stage when a lot of things can be difficult. The two major reasons for failure, I think, are one, that the main mean position is wrong, and because of all the things that Jim talked about this morning, and he went into that in some detail. All the spot searching hasn't worked very well. So you can do, on the previous thing here, if you want to search for the beam center, you can click there and it'll do a grid search on the beam center. And that's sometimes useful. If it doesn't work, what can you change? You can also try indexing on single images or different images. Maybe the image one, it chooses image one. Image one sometimes is horrible for some bizarre reason. Maybe if you index on image 2 or image 10, it'll work much better. There's a maximum cell edge, which is up here, which sometimes, that thing there, which is sometimes useful to change. The spot resolution, there are a whole load of parameters changing the spot. If you don't like which spots it's chosen, and I still complain frequently about the MOSFLM spot finding algorithm. Often there are lots of spots on the images that are perfectly obvious to me, but for some reason it doesn't like them, and I never. Even Andrew doesn't understand why it doesn't choose them. But you can fiddle with the spot selection criteria. One thing here is going back to the reversed phi. If indexing works on a single image but not on two images, you should think about whether you've got a phi going in the wrong direction, because that will not work. That'll work on one image and not others. How do you know if it's worked? You need to examine critically the observed pattern, the predicted pattern superimposed on the observed pattern. So here's an example which is actually multiple lattices. And you can see you probably can't see it. The boxes, which are little yellow boxes, mainly, which are almost invisible on this projector, are the predicted pattern, and the crosses are the found spots. And you can see that there's a lot of found spots which are not predicted. There's something wrong there. The colouring of them, one thing to look out on that is red ones are overlapped. So in this case, there are a lot of overlaps because it's got two lattices. It's predicted a much larger mosaicity, and then the spots are running into each other. So if you integrated it just like that, you'd lose all this data, and that would get seriously incompleteness. And you have to do something about that. Now you can fudge the parameters a bit to cheat, to artificially fix the mosaicity smaller than it really is, just to get it to work. And you can fix parameters that determine the spot size. But at least you should be aware that you're losing a lot of overlaps, and you can see that very clearly. A new feature in MOSFLM, which is very much under trial, is the indexing multiple lattices. So this case is a clear case of two lattices, and it's given two lattices, and now we've got much better positional residuals. And you can display the different lattices, and you can see that then if you display both lattices, you can see it now predicts all the spots, really. But there's a real warning here. This is a very experimental, and it works if you have 2 or maybe 3 decently separated lattices. It will not work if you've got horrible smeary spots where you've got 100 lattices, really. And it may not work in other cases. It's still... And indeed, in some cases, if you've got a weak second lattice, it may actually work better to ignore it than to try and process it. I don't know why that is. That's probably the program not being very adequate. So, yeah, multiple lattices. It's quite common, and the best thing is to find a better crystal, to be honest. But if you have this is worth trying. But there's absolutely no guarantee of success, so be very cautious. The next one down on here is strategy, and this is useful before you collect the data. Obviously, after you collected the data, it's a bit late. So you've collected 2 or 3 orientation images, you've managed to index them, and you want to know some things about it. And the most important thing is, where should you start data collection? And I always think it's worth starting at the right point rather than randomly, because in case that means you have a better chance, if something does go wrong halfway through the data collection, you've got a better chance of getting a complete data set. You can also use this to explore reflection, maximum rotation range. Note that 1 degree is almost always wrong, but is surprisingly persistent in certain circles. I hope that this is vanishing rapidly. There's also complicated things you can use where if you collected part of the data on one crystal, you can try and work out which bit you should collect on the next crystal after you've indexed it. And the tutorial goes through some of these things, but it's a bit complicated. Notice this is sensitive to the parameters you set in the indexing stage, the point group, because that'll tell you the completeness, the mosaicity, and the maximum resolution. So this is an exploration thing, and I know there are automated processes for working out what your strategy should be, but this is an interactive way which is actually quite useful in some cases. The general strategy in MOSFLM is to refine the unit cell before you go into integration, and then fix it during integration. And the reason for that is because the units on a narrow edge of data, certainly in low symmetry, the cell dimensions are not all well determined. So it's better to take 2, 3, or 4 wedges of data. I mean, you could take all the data, but it takes a long time, and refine the cell first. So it'll automatically select 2, 3, or 4 wedges depending on the symmetry. In high symmetry, it'll just take 2, and P1 it'll take 4, I think, because you've got more parameters to refine, you need more data, more spread out. And then it integrates them and refines the parameters, all the detector, instrument parameters, and the crystal parameters. That is the unit cell and the orientation. And what are you looking out for? You click on there to run. What are you looking for? You're looking at the central spot shape, which should look reasonably nice and should be centered. And you want the parameters to be reasonably sensible, and particularly the mosaicity should look vaguely sensible. And if it refines to 0, it is something is wrong. This doesn't work very well at low resolution. Lower than about 3.5 angstroms, it's not very reliable, and you probably do better to just index on a lot of images and use a cell from those. It's actually quite hard to get a really good estimate of unit cell, which it comes into later processing. So then finally we actually get to the integration step. And again, it'll automatically choose all the images. It's maybe sometimes a good idea to integrate just the first few, just to get the parameters to settle down, and then restart it again with all the images. It runs automatically, it writes the data into a file which you can change the name of. If you've got multiple lattices, you have to do it separately for each lattice. And then when you're looking at it, what you want to see is that the various parameters are varying smoothly. They're not suddenly jumping, they're not going completely wild. And that's a hard thing to pick up for programs to pick up, but you can see if things go really haywire. And again, the mosicity refining to 0 is a good indication that something horrible is happening. It shows you the central spot shape for each image and the spot shapes across the detector in different regions for each block of images. It's typically about 10 images or so. This shows you the true horror of spot shapes, which you hadn't really noticed when you looked at the images before. But surprisingly, you can still get quite good data, even with horrible spots sometimes. Note that in MOSFLM, the spot size is automatically chosen. You don't have to input it, although you can change some parameters that affect it, which I'll come to. So the integration stage is usually pretty good. There is a parallel. You can parallelize it to make it go faster, actually, now, from the interface. And then it writes each bit out into a separate file. At the top of the window, after you've done the integration, it's hidden in there. There are a couple of buttons marked Quick Sim and Quick Scale, and they will do run the downstream processing programs. Quick Sim just runs point lists to try and find the point group, and I'll come back to that later. I'll describe that in more detail later. Quick Scale runs the whole data reduction pathway. That is, it runs a new program called FetList to combine lattice files if there are multiple lattices, and then pointless, aimless, C-truncate, and free rflag. And I'll describe this in more detail later. And then you get this output window, which is the same as you get from CCP4I, with the summary table and lots of graphs and things you can look into in more detail. In fact, including the actual raw log file there. So that's quite. In fact, you've got a load of options in this one of the settings pull downs here, which you can control many of the parameters of the data processing, the data reduction steps. But I'll describe in a minute the use of the interface from CCP4I, which gives you a few more options. Although I have to say, actually, this covers nearly all the things you actually want to do in real life. There are also a lot of other parameters you can change from these pull downs. There are a couple of parameters here which control how big the spot size is. So and it has hints there that tell you what you should do. So if you've got a very crowded diffraction pattern with a high mosicity where everything is overlapped, you can cheat a bit by forcing the spot size to be smaller and the mosicity to be smaller by fixing it. And then the number of overlaps, the apparent number of overlaps has gone down. But of course, you're then only integrating the central part of the spot and not the whole spot. You can get away with it if you have to. So that's really all I wanted to say about MOSFLM. And again, I shall be around this evening and tomorrow if people have any questions about any of this stuff. Now, Spishak did a very good job this morning of describing the scaling and merging step. And I'm going to describe how this fits into the CCP4 programs that do this. And as he said, what we've actually done, we've taken the true, this is the true F squared which we're trying to find, and which is there. We've done it, which is inherent in the crystal. And we've done an experiment where there are lots of effects which are in this Darwin equation. We measured intensity, and our job of the scaling is to invert this process. We need to parameterize the experiment in order to infer F squared and F from the measured intensity. So we're going to model the experiment. The whole data reduction pathway in CCP4 involves a series of programs. First of all, this program FetList for multiple lattices. You can have multiple files from MOSFLM or XDS or wherever to combine data from different crystals or different sweeps of data into point lists, which also determines the point group, space group, and makes consistent indexing. And there's a scaling step which is done in Aimless, which does the same job as the older program Scala. And then we estimate F from I and generate a free R set. And at the end, we have a set of data which is suitable to go into refinement or molecular placement or whatever. In the CCP4I interface, there's this task here, scale merge aimless, which is the one to use for this. It brings up a window like this with lots of options. I should note that at the moment, until I get around to doing it, it does not run vectors on multilattice data, and it's something I need to do. The first step of this then is running pointless, and I should point out that pointless can actually read data from other formats other than the MTZ file from MOSFLM. It can read XDS files, either the integrate or the scaled XDS ASCII file. It can read raw files from Saint. It can read scale pack unmerged files and ShellX files, although in these cases you can't really scale it, but they're probably scaled already, so you don't need to. I'm not sure whether you'd need to, or why you'd want to do this particularly. So these are organised, so that the top here are the main sort of flow options, if you like. So if you click on that, you get some more options about the symmetry determination. The default is to try and determine the Lala group. If you know the data already scaled and you just want to just do the merging in the scaling at the aimless stage, you can click on that, and that lets you output unmerged data as well as merged data. This is slightly redundant because Aimless now automatically decides whether it wants to do something different or significant anomalous. And normally you would run ctruncate to generate Fs from the Is, and you may well want to generate free Rs, and you can incorporate an existing free R set. The input file specifications here, you can have multiple files, and they're assigned to a particular data set. You have different file types, and you can use if you have a reference file, which you might have for the index, I'll come to that. Yeah, okay, I'll skip that. There are options here to exclude data, particularly resolution cutoff and particular batches. Batches are image numbers incremented by a multiple of 1,000 for each block of data, each sweep of data, if you've got multiple ones. Those are typically the only things you need to change. There's a whole load of stuff down here which you wouldn't normally want to change, I think. But you can if you want. Just as a future plug, there is a new interface for CCP4 under development, currently under the name CCP4I2, and that looks different, but there is a data reduction pipeline task which has essentially the same options as we have in there. It just looks a bit different. And it puts its results out in a new flashy format with lots of graphs and things. But this is just an advertisement for things to come, really. So going back to this task here, the first step in here, significant, is pointless. Now what pointless does, apart from combining different files, is to try and determine the space group, the point group and the space group. Now, it's important to remember that when you index the lattice in any of these programs, all you do is find a geometrical lattice which fits the observed pattern with a certain unit cell. And that doesn't tell you anything about what the true symmetry is, because you can perfectly well have a triclinic cell with all the angles very close to 90 degrees, for example. So what pointless does, from the cell dimensions, this is doing some of the things that HKL 3000 does that Zizek talked about this morning, but it's doing it in a different way. It ignores the input symmetry and just looks at the cell dimensions and works out the maximum possible lattice symmetry. That maximum possible lattice symmetry will have a series of rotational symmetry operators along the principal axes, along diagonals, and so on. And for each possible rotation operator, it scores observations, reflections that would be related by that operator if it were present. So here we have a case which is pseudo-cubic. That is, the angles are 90 degrees. All three cell lengths are about the same. So this is the cubic nth bar 3m point group. 17 symmetry operators, including the identity, and it scores how well they agree on using normalized intensities, actually. So it scores them with an R factor and with a correlation coefficient, and then a Z score on the correlation coefficient and a likelihood estimate on the correlation coefficient. So you can see this case, really, there are only 3 good scoring operators, which are the two folds along HK and L. This is actually orthorhombic. They have a low R factor, a high correlation coefficient, and everything else is not good. And this table of the different operators is really useful when you've got pseudosymmetry, because you can see if some of the operators are better than others. Once you've got these operators, they get combined in all the possible combinations to score the point groups. And then finally we score the axial systematic absences to see if we can find screw axes along the axis. Note that it's very common if you rotate around one of the axes, which you may well do by deliberately or by mistake, you won't get the data along one of the axes because it's in the bind region, and then you don't have any information about that. So here's a case where this is the combination of all the possible cases. This is a different case. This is a pseudo-hexagonal one that's actually C-centered orthorhombic. And you might notice actually there are 3 possible settings of that, which are 60 degrees apart. And when the scores, again you get this table, you get R factors, but as well as scoring the operators that are present in that Lie group, it scores the operators which are present in the lattice symmetry but not present in that point group, and those count against that group. What can go wrong? It's not always right. The space group is a hypothesis. You should never ever get caught in the trap that early on in an analysis you decide what the space group is, and then you stick to that through thick and thin. It may be wrong. Do not believe your conclusions. Pseudosymmetry and twinning, which will often give you too high a symmetry, because and you have to be aware of that possibility. So if the data look twinned, then you better look at these rather carefully. If you take the output straight from MOSFLM, it's unscaled, which is why I use correlation coefficients, because they're less sensitive. But if your crystal was dead at the end, those dead reflections will not agree very well with the ones earlier on, and then it'll apparently give you a much too low symmetry. And if you think that's happening, then you can just try the first part of the data, or you can actually run its scaling in P1 and then put it back into pointless. One track for the unwary: if you put data through this process and it didn't have it, let's say it's orthorhombic, and it didn't have data along one of the axes, it will be labelled as space group P222, which is almost certainly wrong because it's very rare. 25% of structures are P211, I think. And you should be aware of that. You need to determine the space group later. And it's very easy when doing molecular replacement to try all the 8 possibilities in orthorhombic, for instance. And I would always do that, even if you know what the space group is, because it provides a nice control. You can combine multiple files. Here is a complicated case, 5 runs of MOSFLM on different, it's actually all the same crystal, but so we had 3 on the peak and one on the inflection, one on the remote, and I've identified them as a dataset name, different dataset names, which means they get scaled together but then split out separately in the end. And this is quite flexible for this. Alternative indexing. If you have a point group which is lower symmetry than the lattice point group, then there are alternative valid but non-equivalent indexing schemes. And these are also, this is related to where you can get monohedral twinning. That is, those symmetry operators that are not present in the true point group are possible re-indexing operators. So in P3, which is the most common one, the most complicated one that we would come across probably, you've got 4 schemes. You can interchange H and K and you can invert them. Now, all of these are correct, but they're different. So on your first crystal or first bit of data, you can choose any one you like, but you better be sure on your next crystal that you index them consistently. So if you have a series of multiple reflect files, it'll compare each one to the previous one. But if you have an external reference, which can be a reflection file or a coordinate file actually, you can ask it to match the index to reference, and you can give it a file here, and then it will compare all the data to that file. The warning on that is it will assume that the space group given here is correct, and it will not redetermine the space group. You can actually also tell it to use this file as a reference file for an analysis, which I'll describe later. This is important. If you get that wrong, you can really mess up your data. I'm rather impressed by the algorithms that Kai and his colleague came up with for resolving this ambiguity in the case of XFEL data, which is much more difficult because you have little tiny fragments of data. This algorithm works well with where each bit is pretty much complete, but will not work in... None of this stuff works well for things like XFEL data, where you've got a very large number of very small bits of data. They really need different algorithms to handle that sort of thing. Spishek went through this morning why reflections on different scales. I'm not going to repeat this, but just to point out that, again, this is precision versus accuracy. This scaling process makes the data internally consistent rather than correct. And there's an important distinction we discussed this morning. But after you've run that task that I showed, it'll run through the scaling, and it gives you a considerable amount of statistical output. You can look at it from the CCP4, either the view job results news file, which gives you this thing, same as the output from QuickScale, which gives you the graphs in the summary, and you can look about that. It's probably the easiest thing. You can just look at the graphs from there, and there are some other plots here which might be interesting, which I don't have time to describe. You get the output from each program here, so you can also look at the details of the pointless output there. You get out a table 1, which contains a lot more than John's table 1 that he showed this morning. But the sort of things... One of the things I like is actually having the inner shell data as well as the outer shell data. I think that's quite informative sometimes. You get a lot of graphs. You get resolution things, you can look at those. What are we going to look at? What are the questions? How do we measure things? We're going to be looking at... There are 2 sorts of things we look at here. Well, there are lots of things, actually. The questions, are there some parts of the data we really should reject? Was the crystal dead at the end? If we cut it back from the end, maybe it would be better. And we had a long discussion this morning about resolutions, which I'm not going to repeat either. What are the measures of quality? Signal-to-noise estimates. And again, these were discussed. Assorted R factors. Incidentally, one reason why these R factors that we calculate here are completely different from the R crist is that the thing under the bottom, the sum of intensities, when you do it in shells, that can go down to 0, and that all can actually go negative. So that means that this R factor, as you get weaker and weaker data, will go up to infinity, in principle. The R crist is based on Fs, and Fs can never go negative, and in fact, if you've gone through the French and Wilson truncate procedure, they never even get close to 0. So they plateau as you get noisier data. The R factors go up and then they flatten off. So it's completely different behaviour, and again, is another reason why you can't compare these things. Just because they're called R doesn't mean to say they're the same. And then you can do correlation coefficients. So Kai went into this in great detail. So, but what I do like to look at is the analyses against batch, which is essentially image number, or time, or dose. They all sort of go linearly with it. So what can you look at? You can look at the scale factor. And this is a case of two lattices, that multi-lattice one we saw here. It plots two things on the scale factor. It plots the scale at 0 phi, the basic scale, and the mean scale, which is after you've added in a relative b factor as well. So you can see these deviate when the b factor is large. So here's two lattices. The first lattice is quite strong. The second lattice is much weaker and gets very weak at this point. You see the scale factor is going up to even at low resolution to 15. You can look at cumulative completeness, and that'll tell you whether you can afford to cut back the data from the end. How am I doing?
You have about 5 minutes.
I'm not going to get anywhere near the end, but that's all right. Okay, same thing here. One thing I think is really nice, is something I've added very recently, is if you give a reference, e.g. calculated structure factors from your best model so far, you can compare by R factor and correlation coefficient how well the data as a function of batch agree with that. And this is a case that I wrote it for, really. It's 5 crystals, and you can see that this crystal is good, the beginning of this crystal is good, the beginning of this crystal is good, these crystals are terrible, and if you just choose those bits, you're going to get a much better set of data. Some problems about feedback, maybe, but I think it's all right. I'm not going to discuss this half because Kai went in that. It does print out anisotropy as a function of resolution measured in cones, both on I over sigma and in CC half. I think that's very informative. I just want to point out that thing. If the referees ask you to cut back your resolution, why would you think that would improve your model? I would quote that back to them. I don't have time for outliers. You've got things for detecting anomalous signals, which are rather useful, I think, including the CC half, the CC anon, but a few other things like scatter plots. And actually, the CC half, of course, is a scatter plot, essentially, slope of a scatter plot. And finally, we infer F from I, and it looks at intensity statistics, look for twinning. So, sorry, as I said, I could have easily taken 3 hours over this. You've got a whole load of decisions. You've collected some data, you run it through the processing program. All these statistics tell you something about the data you've just collected. And you can now make some decisions using your experience and wisdom. What's the point group? What's the space group? You may not be able to determine that. What's the crystal dead at the end? Is the data set complete? Somebody was showing me a paper they were refereeing, but I was asked for the comment on the table 1 with a 60% complete data set. That is not usable in my opinion. Do you want to cut back the resolution? You want a comparison. Typically we go to a synchrotron with dozens, hundreds of crystals and collect lots of data sets and then think about them later. And you want to choose which ones you want. And should you merge multiple data sets? And all these are decisions you can make based on this, but also from the downstream processing. If you've got multiple possible data sets, take them through to molecular replacement and refinement and see which one gives you the better statistics and nicer maps. There's nothing... Computer time is cheap. Your time is expensive. Is there anomalous? The twinning. Twinning you really need to watch out for. Try different things. Yes, this is what I'm saying. Data processing is not something you necessarily do once. Once you've got the solution, you can start going back and thinking about how could we improve this? Can we get a better crystal, better data? Right. That's it.
Another slide?
I have an acknowledgement slide.